Yes. Next method, preparation of alcohols. Ninth method, by the reaction of acid derivatives. Rather, we'll take one acid derivative by the reaction of esters. By the reaction of esters with Grignard reagents. Reaction of esters with Grignard reagents. Madam, esters of methanoic acid means formic acid. Esters of methanoic acid react with Grignard reagent and lead to the formation of an aldehyde which on further reaction with Grignard reagent gives a secondary alcohol. Gives a secondary alcohol. Write down equations. HCOOR. This is the ester of methanoic acid. Reacts with Grignard reagent R-MgX. This will lead to the formation of aldehyde and byproduct is alkoxy magnesium halide. Now this aldehyde formed, this will further react with Grignard reagent and lead to the formation of secondary alcohol, and this is the method of preparation we studied last time. Aldehyde will further react with Grignard and lead to the formation of secondary alcohol that we'll find in the last method I told you last time. Next paragraph. However, esters of other carboxylic acids, react with GR, react with Grignard reagent to give a ketone which further reacts with Grignard reagent to give a tertiary alcohol. Write down equation. Now this is an ester of an acid other than formic acid, right? It means this R is not hydrogen. Reacts with Grignard. This will be the ketone formed. In this case, ketone will be formed. Note down the equation. Now this ketone will further react with Grignard reagent and lead to the formation of tertiary alcohol. Again, this is the method which we did last time, we studied last time. So first ketone will be formed and ultimately tertiary alcohol will be obtained in this case. Next paragraph, write one more sentence. Primary alcohols cannot be prepared by this method. Next, rather last method of preparation. By hydroboration, oxidation, of alkenes. Hydroboration, oxidation of alkenes. This is a very important method. First, you write what I'm dictating you. After that, I'll explain with an example, right? First, keep on writing. That this method involves two steps. This method involves two steps. In the first step, diborane acts as an electrophile because it is electron deficient and makes electrophilic attack on C double bond C, makes electrophilic attack on C double bond C of alkene. I hope you know all boron compounds are electron deficient compounds. Since they are electron deficient, naturally they will act as electron lovers. It means they will act as electrophiles. And wherever there's pi bond present, electron density is high. This is the reason diborane attacks carbon-carbon double bond of alkene, and it is acting as an electrophile in this reaction. Yes, continue. Boron forms a bond with that carbon atom of C double bond C, which is attached to more number of hydrogen atoms or a shorter alkyl chain or which is less alkylated. Full stop. At the same time, one hydrogen atom shifts from boron to the other carbon atom of C double bond C. Process repeats itself and finally a trialkyl borane is obtained. This is called hydroboration of alkene. For example, now I'm taking up an example and at the same time I'll explain what I have dictated you, right? Keep on writing. Propene. In fact, diborane is B2H6 and B2H6 is the dimer of BH3. So we can take BH3. As I told you, boron compounds are electron deficient. Boron has 6 electrons in the valence shell. It doesn't have a complete octet. This is the reason this will attack carbon-carbon double bond. Now, after this, do not write anything on the product side. Wait and try to understand. I told you boron of BH3, diborane, will form a bond with that carbon atom which is linked to more number of hydrogen atoms, or which is less alkylated, or which is linked to a shorter alkyl chain. It means in all the cases, it comes out to this carbon atom. Boron will form a bond with this carbon atom. Double bond will change into a single bond. So this will be CH3, CH, CH2, BH3. Don't write, please. Then you have written that at the same time, one hydrogen atom from boron shifts. One hydrogen atom from boron shifts. Where shifts? Shifts to the other carbon atom of C double bond C. The other carbon of C double bond C is this one. So one hydrogen from boron will shift to this carbon atom. One alkyl chain is attached to boron. This is alkyl borane. One hydrogen of BH3 is replaced by alkyl. Similarly, one more will be replaced, then ultimately one more will be replaced, and last we get a trialkyl borane. So further, this will react with CH3, CH double bond CH2. This boron will attack this carbon atom. As I told you there in the first step, this boron atom will form a bond with this carbon atom. I'm writing this. This is BH2. But at the same time, one hydrogen from BH2 will shift to this carbon atom, and remaining part will be attached like this. So first, one hydrogen was replaced by alkyl. Next, two hydrogen atoms have been replaced by alkyl chain. This I can write like this. These two alkyl chains are same. So I can write it like this. Twice BH. This will further react with alkene, and this third hydrogen atom will also be replaced by alkyl chain, and we ultimately get trialkyl borane. Now please note down, I'll complete the reaction. Note down everything. This is trialkyl borane. I'm waiting for you to copy it. Yes, further write down. In the second step, trialkyl borane is oxidized with alkaline H2O2, alkaline hydrogen peroxide, to give an alcohol. Write the equation. This is alkaline hydrogen peroxide. This leads to formation of 3 molecules of alcohol. Product is 1-propanol. Plus we get boric acid. for the right one. Overall, this method involves addition of water to an alkene according to anti-Markovnikov's rule. Both these steps can be combined together and the reaction can be represented as follows. So I'm combining both the steps together and writing in one equation, one equation, but I'm changing the example. Just for practice, I'm changing the example. I've taken 2-pentene as the reactant. Above the arrow, number 1, BH3, number 2, H2O2, alkaline. So what you have to do is you have to add water to the double bond, but you have to follow anti-Markovnikov rule, anti-Markovnikov addition of water. Think of 2 parts of water as H plus and OH minus ion. OH minus will go to that carbon which is linked to a shorter alkyl chain. This is linked to a shorter alkyl chain. OH will come to this carbon atom. Product is 2-pentanol. This is the product obtained. So these were 10 methods of preparation of alcohols. Next topic. Preparation of phenols. First method. From aryl halides, ARYL, aryl halides. We already done that. Within brackets, write down CDOW, Dawes process. Dawes process. Also write down, this is a commercial method of preparation of phenol. Second method, from diazonium salts. That diazonium salts react with dilute acids or warm water to give phenol. Write the equation. How to prepare diazonium salt we did in alkyl aryl halides. This diazonium is reacted with water at high temperature. Just slight warming is required, or we can use any dilute acid, dilute HCl, dilute sulfuric acid. This is acidic hydrolysis. Gives phenol plus nitrogen plus HCl. Next, third method of preparation. From cumene, CUMENE, from cumene. If you want, within brackets, write down commercial method. This is also commercial method of preparation. Means industrial method. Cumene is prepared Cumene is prepared by a special Friedel-Crafts reaction between benzene and propene, in the presence of phosphoric acid. In the presence of phosphoric acid. Try the equation. Benzene plus propene in the presence of H3PO4 we can prepare this compound by Friedel-Crafts alkylation as well. But on large scale, on commercial scale, same scientists, that is Friedel and Kraft, they developed a special method to prepare cumene at low cost. They reacted benzene with propene in the presence of phosphoric acid. Product obtained is cumene. Another common name is isopropyl benzene. IUPAC name is simple. IUPAC is 2-phenyl propane. 2-phenyl propane. Now further write down. Oxidation of cumene with oxygen followed by reaction with dilute sulfuric acid gives an equimolar mixture, 1:1, equimolar mixture of phenol and acetone. Phenol and acetone. It means we can say that acetone is a byproduct of this industry. And the equation. Cumene first reacts with oxygen to form this product is called cumene hydroperoxide. This is reacted with dilute sulfuric acid and leads to formation of phenol and acetone. Phenol and acetone. Next and the last method of preparation, number 4, from sulfonic acids. From sulfonic acids. When a mixture of solid NaOH and solid sodium benzene sulfonate is melted. We take the mixture of these two solids and strongly heat so that the mixture melts, is melted, sodium phenoxide. Sodium phenoxide is formed, which on hydrolysis gives phenol. Gives phenol. There will be three equations. This compound is benzene sulfonic acid. Benzene sulfonic acid reacted with aqueous NaOH. This is sodium benzene sulfonate. Sodium benzene sulfonate means sodium salt of benzene sulfonic acid. In the second step, this product is taken in the solid form, mixed with solid NaOH. Remember, in the first step, it is aqueous NaOH. Now this is solid NaOH. Mixture of these two solids is strongly heated so that this mixture melts. Melt to melt, oblique heat, gives, you know this compound, this is sodium phenoxide plus N2SO3, that is sodium sulfite plus water. In the last step, sodium phenoxide is subjected to acidic hydrolysis and we get phenol. Ultimately, phenol is obtained. Next topic. Physical properties. These are physical properties of alcohols and phenols together, right? Number one, physical state. Number one, physical state. Alcohols up to C11, up to 11 carbon atoms. Alcohols up to C11 are colorless liquids with a distinct smell and a burning taste. Higher alcohols are colorless, waxy solids. Colorless, waxy solids. When you touch candle, candle is wax. When you touch candle, it has a special feel. It gives a special feel. Higher alcohols give the same type of feeling. Phenols are colorless liquids or solids when pure, but they generally become reddish brown reddish brown due to aerial oxidation. So if phenols are allowed to stand for a long time, slowly they will get oxidized with a oxygen present in the atmosphere and will lead to the formation of compounds called quinones. Sorry. And these quinones are brown in color. That is second property. Boiling points. Boiling points. In general, remember one thing, wherever OH group is present, there will be hydrogen bonding, and hydrogen bonding always increases boiling point. Also, if number of if number of OH groups is more, hydrogen bonding will be stronger, boiling point will be high. So write down. Boiling points of alcohols and phenols are higher than hydrocarbons, ethers, and halides of comparable molecular weights. Comparable, similar molecular weights. This is due to extensive hydrogen bonding in them. BP increases with boiling point, increases with increase in molecular weight and number of OH groups, right? Because if molecular weight increases, surface area will increase. Surface area increases means van der Waals force of attraction will become stronger. And if number of OH groups increases, hydrogen bonding will become stronger. Further write down. Boiling points of isomeric alcohols decrease with increase in branching. Decrease with increase in branching. Within brackets write down Y. Y means reason is same as we discussed in case of alkyl halides. Third property, solubility. Solubility. Alcohols are soluble in water due to the formation of hydrogen bonding with water. Hydrogen bonding with water. Solubility decreases with increase in molecular weight due to increase in surface area. Due to increase in surface area. Solubility of isomeric alcohols increases with increase in branching due to decrease in surface area. Phenols have very low solubility in water due to their large hydrocarbon part. That aromatic ring is quite big. That's why solubility of phenols is low. All alcohols and phenols are soluble in organic solvents like benzene, ether, etc. Last property, number 4, density. Density. Monohydric alcohols are generally lighter than water, means their density is less than 1 gram per cc. Lighter than water, although their density increases with increase in molecular weight. Next topic, chemical properties of alcohols. Chemical properties of alcohols. Reactions of alcohols can be divided into two categories. Number 1, reactions involving write like this, reactions involving OH bond cleavage. OH bond cleavage. It means those reactions in which bond between oxygen and hydrogen will be broken. Number 2, reactions involving CO bond cleavage. Now write like this, CO bond cleavage. So we are starting with the first category, that an A part. A part, reactions involving OH bond cleavage. See, some properties of alcohols and phenols will be common. They'll be studied together. Some are absolutely different. They will be studied separately. Like in this category, the very first property is common in alcohols and phenols both. So that will take up together. So write down first property under this category, acidic nature of alcohols and phenols. Acidic nature of alcohols and phenols. Look here. Oxygen is more electronegative than hydrogen. That is why bond is polar. This carries delta negative and this carries delta positive charge. This polar bond breaks heterolytically and releases hydrogen as H plus ion. And compounds which liberate hydrogen as H plus ion, they are acidic in nature. They react with bases to form salt and water. They react with reactive metals and lead to the formation of salt and liberate hydrogen gas. So all this type of properties are shown by alcohols and phenols. Now write down. Oxygen is oxygen is more electronegative than hydrogen, so that OH bond is polar and breaks heterolytically to liberate H plus ion. That is why alcohols and phenols are acidic in nature. Next paragraph. Due to acidic nature, they react with reactive metals. They react with reactive metals like sodium, potassium, calcium, aluminium, etc. to form salt and liberate hydrogen gas. And liberate hydrogen gas. Write down two equations. One is the reaction of alcohol, the other is reaction of phenol with a metal which may be sodium, maybe potassium, maybe calcium. These should be reactive metals. Lead to the formation of salt. Alcohol leads to formation of sodium alkoxide. Phenol will lead to the formation of sodium phenoxide. These are salts. In both the cases, hydrogen is produced. For the write on. In these reactions, low molecular weight alcohols up to C11. I told you C11, up to C11 they are liquids. Up to C11 liberate hydrogen gas in the form of bubbles. That is called effervescence. In the form of effervescence. That is why reaction 1, label it reaction 1 and 2. That is why reaction 1 can be used as a distinguishing test for alcohols up to C11. This reaction cannot be used as a distinguishing test for higher alcohols and phenols which are solids. Next paragraph. See, you know it very well. A gas will be evolved in the form of bubbles, in the form of effervescence, only through a liquid medium. Like when you open the bottle of a soft drink, Coke, you see effervescence. But if hydrogen or any gas is produced, but this escapes through a solid, this type of effervescence will not be observed. Right? Next paragraph. Phenols react with aqueous NaOH to form salt and water, while alcohols do not. Write down two equations. Phenol with aqueous NaOH alcohol with aqueous NaOH. Write this equation and just one more sentence. That's it. Say, on the basis of reaction with metals, I said alcohols and phenols both are acidic in nature, right? Now you know acids react with bases to form salt and water. If both are acidic compounds, they should react with base that is NaOH and form salt and water. But only phenol reacts to form salt and water. Alcohol does not. What does this prove? This proves that phenols are stronger acids compared to alcohols. So write down. This proves that phenols are stronger acids. Phenols are stronger acids than alcohols. than alcohols. Right, that's all for today's class.